Today is 2025, 3rd of April. Another linear regression. Last time what we talk about is how to determine each input variables and how to test significance of linear regression model. So if with F test statistics, if it is smaller than significance level, if it is smaller than significance level, then which means if it is bigger than significance level, which means smaller than because when in null hypothesis, beta 0 equals to beta 1 equals to 0. So if it is smaller than significance level, maybe my wording is wrong now. Smaller than let's say normality distribution G alpha over 2, then in that case, it is not significant, which means even you change the input variable, it doesn't affect to output variable, so it is not needed. So we did significant test of model of test of significance of each input variable, which is changed input variable doesn't change output variable. Today, we will talk about another test concerning regression coefficient, which is H0 equal to beta 0 equal to 0, which means each of the variables, each of the coefficient variables are 0 or 1. Test statistic will be Pj equals to beta j hat over Fe b j hat. So if you feed the Pj equals to beta 0 hat over Fe beta j hat. And for Fe, you can calculate Fe beta j hat by MSE multiplied by X transpose X minus 1. And you will compare it with compare it with significance level. So, and for more critical value, critical value. Yeah, critical value. Significance level is just alpha equals to 1 or something. And alpha will be probability. In this case, critical value. You should compare with critical value. No, I missed thing. And I will more give you the more situation. This situation is like this. This is about like we have linear regression, which is y equals to b0 plus b1 x plus epsilon. Because of epsilon, we will say epsilon follows standard normal distribution, which is mean is 0 and yep, okay. Then let's say we get the sample 100 samples. When we do first sampling, we do first sampling, we get 100 numbers. And second sampling, we also get 100 of numbers. And we do n sampling. And what we can get is we will get different beta 0 hat and different b1 hat. Each of it, we will get beta 0 hat and beta 1 hat. And based on that, what we can get is beta zero has some beta zero has we'll get if we repeat this trial, we will get beta zero hat and beta one hat distribution. It will be something like beta zero hat follows normal distribution of something. Beta one hat will follow normal distribution of something. If we do an n sampling, and for each sampling, if we get beta zero and beta one hat, we will get such values. And the test, what we are doing is using this Pj equals to beta j hat over Se Bj hat. So checking whether in each of the cases, specific cases, this T0, Tj, some B0 or B1 hat is 0 or not. And we can get those values by calculating MSE over MSE multiplied by x transpose x minus 1, which is we can calculate it. Originally, we should calculate it by using this covariance of beta hat equals to sigma squared multiplied by x transpose x minus 1. But in this case, we don't know sigma squared. So we change it to MSE. What is MSE? SSE over SSE divided by n minus 2, if I'm correct. SSE is, you can calculate it by y minus y I hat sigma, y minus y I hat squared. So we just replace it using MSE. So if we calculate, when we are going to calculate it, after calculated, we can compare it with, because it's T distribution, 1 minus alpha over 2, which is in this case, both sides, alpha will be significance level, and also with given freedom, we will determine the test statistics between critical value, which is bigger. So each of the value, whether each of the value is significant or not, whether each of the value beta 0 1 hat or beta 1 hat is significant or not. Okay, when we calculate x transpose x minus 1, which is this part, actually this is covariance matrix. X transpose x is covariance matrix, and important part is there is inverse. We should be able to inverse it. So if you are going to calculate SE squared beta 0 hat, then you can calculate it by MSE multiplied by, this is because covariance matrix, think of it, it has everything, it has if it is let's say beta 0 only beta 0 and beta 1 exist. Beta 0, beta 1, beta 0, beta 1. Then this part x00 and x11 will be covariance. Variance of beta 0 and variance of beta 1. In this case, we can calculate SE squared beta. Yeah, let's say SE squared beta 0. It will be MSE over MSE multiplied by x00. For standard deviation, we can root it. So root MSE multiplied by x00 will be SE, value of SE. So based on that, we can, based on significance level, we can determine whether it has problem or not. And important thing is when you read T distribution, when you want to calculate significance level, critical value, then you should know both significance level and degree of freedom. If you want to really try to calculate it, maybe we could try, let's say, y. It will be 3 theta y equals to 1, 2, 3, 4, 5. And with this, we can make y hat. If not x, we can make y hat. And we can minimize the y minus y hat. In this case, then MSE will be 0. Then each of the variance will be also, in this case, each of the variance will be each of the variance, if we say x equals to 1, 2, 3, 4, 5, y equals to 1, 2, 3, 4, 5, y hat equals to something 1, 3, 5, 7, 9. In this case, each of the variance of MSE, we can calculate it easily by yi minus yi hat squared. And in this case, we can calculate covariance by variance. X transpose X. We can do X and X transpose. Then it will be in linear regression situation, it will be 1, 1, 1, 1, 1, 2, 3, 4, 5, if 1, because in linear regression, we will do beta 0, beta 1. So this will be, in this case, this will be X matrix, A matrix, AX equals to Y matrix, probably. So input variable is 1, 2, 3, 4, 5. And covariance matrix, between covariance matrix, we have this relationship. Or how can I define this relationship? When input is this 1, 2, 3, 4, 5, X matrix for calculating variance, covariance will be this. Yeah, so you can really calculate this Tj equal to beta 0 hat B zeta beta j hat over Fc beta j hat. And we will call this as test corresponding regression coefficient. Yeah, and we learned about another test, which was this is for each of the variable. For that one, it was every variable we use F statistics, it was MSE over MSR or MSR over MSE. I will do it later so we can calculate those values. And next is when we do linear regression using linear regression model, two things that we should check is linearity and colinearity, which is we should check before that. Linearity is this is general linearized model case, which is y equals to f function beta 0 plus beta inside argument. Inside argument is linear combination of linear combination. So we can represent it as matrix, which is like this. And in this case, data will be 1, 2, 3, 4, 5, like this. If you explain it as linear combination, then it is, we say we have linearity. In more general, even this function is, if it is y equals x, then it will be linear regression that we know. But if it is logistic function, then it will be logistic function, and we can go more deeper functions. But even but basically between beta vector and x vector has linear combination. If we make it, then we can think it satisfies linearity. Another thing is it should be not multicolinearity. It should not satisfy multicolinearity case, which is let's say there is correlation matrix. If correlation matrix, if their correlation is super high, let's say there is yeah, x1 and there are x1 and x2, and yeah, think of this beta hat equals to x transpose x minus 1 x transpose y. But if and there are if yeah, SC beta j squared, let's say that example what we already did. In that case, if we get the value of SC beta j hat square, then it will be MFE over m minus 1 SC square xj over 1 over 1 minus rj square. One of the term becomes this one. And problem is, if Ri squares value goes to 1, then it goes to infinity, which means you can't find the value or the covariance of beta j hat gets super bigger. In this case, we say multicolinearity is super high. In this case, it gets problem. So in linear regression, I will look through this more deeply. I think multicolinearity should be, should be related to correlation and invertible matrix. For this part, I will explain you next time more deeply. And so just remember that we should check linearity and multicolinearity using this VIF. So if this regression formula, each of regressions Ri gets super bigger, that you can't use how to calculate. You can't use linear regression. So get back to it. Then let's say if we are able to do linear regression because it satisfies both of conditions. Then after do a linear regression, what we can do is goodness of fitting. This is actually related with R2. So only think of train data, how well fit it is. And in this case, we don't think about test data set. So for goodness of fit, what we're using is R2. When one-dimensional case, it is related with correlation coefficient, which is SSR over SST, or same as 1 minus SSC over SST. And there's also adjusted R2. There's also adjusted. Adjusted R2 is about adding more input variables to the regression model, increases R2, and it will never reduce it. Adjusted R2 is, you can get it by just added degree of freedom, which is 1 minus SSC, same. Basically, SSC and SST same, but divided by n minus 1, and SSC divided by n minus p minus 1. So penalty, you are giving penalty on the number of input variable by n minus p minus 1. So adjusted R2 may actually become smaller when another input variable is induced to the model. So let's think about if you get a lot of input variables, then a lot of input variable, how it will affect it, you can check it. And so if R2 get higher, or get smaller. And we not only good fit, but we can also use another performance metrics such as we call it MSE. With this is different with this one, which is we just divided by yi minus yi hat squared over n, and absolute error, which is yi minus y hat, it's an absolute value over n, and there is also median absolute error, which is there will be or yi minus yi hat value. Let's say we're using this example. in this case 0, 1, let's say y has 1, 3, 5, 6, 9, then there will be 0, 1, 2, 3, 4 different. From this, we are getting median value. Okay. So if we draw what linear regression means, right? And for each of these, you can think of EY equals to beta 0 plus beta 1 x, and each of normal distribution, each of y point follow y, each of y point follows normal distribution of B1 xi B1 xi plus B0 and sigma squared. So we can check linear relationship by scatter plot. In scatter plot, yeah, there was 4 type of visualization. For linear relationship, you can use scatter plot. And the other three thing I mentioned it in last videos, scatter plot and what was it? I will tell you next time again. And for linear, for high correlation, I will talk about this again. It says, and high correlation and covariance. Covariance is you can calculate it by x minus x bar square over n minus 1 sample variance. And let's say, just organize the relationship again. Correlation equals to covariance x comma y over sigma x sigma y. So this is R2 covariance relationship. I already talked about correlation problems. Let's go more specific. Let's say output values of two cases are quite similar. Like if we predict y hat here as 13579, but let's say 13589 is another y2 hat case. Then in this case, beta 1 hat and beta 0 value will be quite similar because x1 and x2 are highly correlated. Explained variance by x2 is also explained by x1, which is coefficient of x2 is quite unstable. Then in this case, beta hat, this part, x transpose x, will be ill conditioned such as non-determinant is not exist, maybe. There should be two sample, but it's actually one sample. I'm not sure it's a good example, but 1.001, and not sure how can I define this? But then we say it's a post. So we can't make determinant, so we can't calculate it. So in least square method, VIF, as we can detect the multicolinearity. I will write down it again. Okay, this is covariance beta j hat, which will be able to write as FE hat FE squared beta hat j. Then this will be MSE, because we cannot use sigma square, we use MSE, X transpose X minus 1. Then if we calculate this stuff, then MSE over n minus 1 SE square xj multiplied by 1 over 1 minus Ri Rj square. This part come out. So if it Rj square, which is R2 square of that, the variable gets high, then we say multicolinearity is too high. I think it's about variance is too high. So I will figure it out next time why it is about multicolinearity. Maybe multicolinearity, if covariance is too high, then correlation is also too high. If we based on this, we can maybe say it like that. And what we should also check is normality. We can also check normality. We can check normality by histogram, which is checking whether there will be let's say original distribution follows normal distribution, but your sample should be also follow normal distribution. If we give with this example, can I think of some examples to normality? I can't connect between two. So if I just explain it, if population follows sample normal distribution, then a sample also follows normal distribution, but maybe it not follows it, then we can say there's some problem in normality. It's not follow normal distribution. Or we can also use QQ plot, which is using quantiles, using both quantiles. So there will be data distribution of original and what we sampled. If both are following normal distribution, it will be y equals to x. But one side is exponential distribution, then it will be like this. And we can also detect normality. It is based on using quantile. Or we can say it is using quantile number, which is PPF function. We can also draw it later. And for homoscedasticity and heteroscedasticity, we can check it, which is check whether all random variables in sequence or vector have the same finite variance. Which is related with residuals. And what another thing we can check is for variance and residual graph. Let's say here. This is variance. This is residual. It will be nice for the residuals if it is like this. So it's line, but sometimes it can be this, or sometimes it can be increased. Then it will be not good between residual and variance relationship. Yeah, so based on residual plot, you can detect if it gets larger later, then we can say it is unbiased but heteroscedastic. And if and if it's like y equals to x, then we can say it's biased and homoscedastic. So if we organize it before doing linear regression, we can check linearity, and multicolinearity. And we can also check, after linear regression, we can check normality, with this QQ plot maybe, and homoscedasticity, with this variance and residual graph, and significance of model and goodness of fit check. Goodness of fit check by R squared, and significance of model by if BJ hat equals over FE BJ hat. And for feature scaling, let's say there is y equals to linear regression, so this is the identity function, and b0 hat plus b1x plus some blah blah blah. Then what we want to do is, even we change some value x, let's say 10x, then there's nothing change in result. This is also interesting topic. When x changed to ax, beta become x over a. I think we should also check it later again what it really happens. Okay, thank you very much.